Hello everyone, welcome to Rotational Dynamics. Now, to make sure that you get familiar with it, I'll have you some analogies with linear and rotational motion. So, if we have linear displacement s, we will have angular displacement theta. Linear and angular. So, if we have initial velocity, final velocity, then we have omega naught and omega. For acceleration, we have angular acceleration alpha. And for mass, we have moment of inertia. So, if we have momentum equals to mass into velocity, we will have angular momentum equals to moment of inertia into omega. Now, we will prove this in a future video, but for now, let me tell you some terms and define some terms related to rotational dynamics that we will have to use later on. First, let's start with a rigid body. So, what is a rigid body? Well, a rigid body is a body in which the particles within that body does not tend to change its position when external force is applied. So, an example could be this marker. If a position, let's say, is within this marker within here, and no matter what I do to this marker, the particle within that marker will stay in that position relative to this marker. Now, for the next one, we have moment of inertia. So, moment of inertia is the inertia experienced during rotational motion. So, what does this mean in practical or in reality? So, let's say if I'm rotating very fast and I suddenly stop. Well, my eyes would still be rotating because of moment of inertia. It's similar to linear inertia when you're in a bus and the bus suddenly stops and your feet stops, but your upper body is still in that inertia phase, that motion phase, and has the inability to change its position, so you just jerk in the bus. Similarly, when something rotates and it just stops, something within that particle, there is the inability to stop rotating or the inability to start rotating. So, moment of inertia, which is denoted by I. This is equals to, well, if we have a rigid body and we have an axis of rotations, let's say y to y dash, let's say the first particle of mass m1 is at a perpendicular distance r1 from y dash, then this is 1 m1 r1 square, and another particle, let's say m2 at a radius r2 plus m2 r2 square, and so on for more particles, and mn rn square. So that means moment of inertia is the summation from I going from 1 to n mi ri square. This is the definition of moment of inertia mathematically. Now, there is one more term, which is radius of gyration or gyration, which is denoted by k. Radius of gyration. Well, before I define what it is, I'll tell you that in a body there is a certain point where the whole mass is acted upon. So that's why you cannot balance the marker from here, otherwise it falls. So you would have to balance the marker from approximately where the concentrated mass lies, where all of the mass of the marker lies, which could be around here. So radius of gyration is basically the point in the rigid body. Let's say this, at this point the center of mass, or the concentrated mass lies in the body, where the whole mass of the body is acted upon, and the radius from axis of rotation to this is known as radius of gyration. So in terms of momentum, in terms of moment of inertia, this is equals to the concentrated mass, or we can simply write m, big capital M, into k square. Now we know from the previous definition that I is equals to m1 r1 square plus m2 r2 square plus dot mn rn square. Now let's say that this rigid body has equal masses for the different radiuses from perpendicular distance from the axis of rotation. So this is just m, this also m, and this is also m. So that means we can take m common. We have r1 square plus r2 square plus dot rn square. Now let's multiply the number of particles. Let's just say there are n number of particles. So if you multiply above, we have to divide. So rn1 square, r2 square plus dot rn square. So the individual masses into the total number of particles, this becomes the concentrated mass of the body. So we have m r1 square plus r2 square plus rn square by n. This is equals to mass into radius gyration square. M and n cancels. So we can also define radius of gyration as the mean perpendicular radius of all the particles. Now, we generally have two different types of rotation. There are of course others, but let's just focus on these two for our SLC examination. So first, from the center of the body. If I rotate like this, then I'm rotating from the center of my body. Now, let's just say this is a pole and this is a body rotating like this. Well, then this marker becomes the axis of rotation for this body. Like this. Now, we will derive the moment of inertia for each of these cases, from the center of body and to the edge of the body. So we will be deriving this in the second video. Thank you for now.